Hi, hello everybody. Today we're looking at 9.6, which is polar equations again, but just more in depth as to what types of graphs polar equations can create. They're actually really cool and not too complicated. I mean, when you initially look at them, they do look more complex than we'll realize that they actually are. So let's start in. When we first look at how to graph um, a, a polar equation, it's basically the same type of idea that you've always had when you initially first go into how do I graph a linear function, how do I graph an exponential function, a quadratic function, a polynomial function. It's set up a table, find the values, plot the points. Alright, so polar equations are given with r equals, and then usually some sort of trig stuff on the right. And in here I have q designating for theta, so don't get confused by that. So basically we have inputs of theta, or this says q, but inputs of theta and outputs of r. So it's the same type of idea with x, y, but theta is the input, r is the output. So we choose theta values from 0 all the way through to 2 pi. See all these very common theta values that we've been working with all year. So we see all those, we input all those, and we see what the outputs are. Okay, if I put 0 into the equation, what do I get for r? If I put pi over 6, what do I get for r? If I put pi, if I get 3 pi over 2, you get a really big table. And then it's just a matter of, okay, now let's graph it. If I go an angle of 0 off of the polar axis right here, an angle of 0 means I'm not doing any sort of angle. My r value is 0, so that's the point right there. If I go an angle of pi over 6, right, if I rotate up pi over 6, where on that line of pi over 6 radians is my point? My point is right there, 2 away. And I do the same thing for all of the others. Pi over 3, where on that line am I going to be? Well, I'm going to be 2 square roots of 3 units away. Pi over 2, that's straight up and down. Where on this line am I going to be? I'm going to be 4 units away. Okay? So we go through and we sketch it all out. We realize that this particular equation for sine of theta is actually the equation of a circle, just written in polar coordinates, which is not one of the more fascinating types of shapes that we can create here. So let's look at some of the more interesting ones. This particular kind, a limation, is given with this type of format right here. That one or this one. So we have a number, plus or minus, a number cosine theta. So this could be, for example, like r equals 3 plus 2 cosine of theta. Or we could have the same type of idea but with sine in it. So this one could say r equals, I don't know, 5 minus 2 sine of theta. Alright, so these two would be examples of different types of limations, and there's 4 different types here. Going from most radical, there's ones that have like a loop on the inside here. So it's literally called a limation with an inner loop. And if we go to the next kind of radical, it's a cardioid or heart-shaped limation. And then even less radical is more just a dimple. It's a dimpled limation. And then over here, just a convex limation. It's almost a circle, but it's not quite. And we can figure out what type. I mean, I can see if something is in this format, a plus or minus b cosine theta. But I can actually see what type of limation it's going to be before I graph it, based upon the ratio of the a to b values. So if the a over b is less than 1, we're looking at an inner loop. A over b is 1, we're looking at cardioid. If it's between 1 and 2, we're looking at a dimpled. And if it's greater than or equal to 2, we're looking at more of this convex limation here. So I just kind of made these two things up here, but let's see what type of cardioid, limation these would be. So I need to look at a over b, so in this case it's going to be 3 over 2, and 3 over 2 is going to be greater than 1, but it's going to be less than 2. So this particular one right here would be a dimpled limation. All right, and then if I came over here, I would be looking at 5 over 2. So unfortunately, my examples weren't very adventurous. Well, actually, this one is, because this one is above 1. It's also above 2. So that means we're looking at a convex limation. So if I put one more example up here that said something like 2 plus, let's say 2 plus 4 cosine theta, then my a over b is going to be 2 over 4, which means I'm looking at a limation with an inner loop. Or if I do one more example and I say 5 plus 5 cosine of theta, this is going to be 5 over 5, which means I'm looking at a cardioid. Okay? Now there's also other types of special polar graphs, and those are called rose curves. And these are probably some of the coolest, and they seem like they would be the most complex kind, but it's really nothing too crazy. The rose curves come from this n value, so it's kind of like when we were doing earlier in the year multiple angles, when you have a number multiplying your theta value. So there's really only like 2 pieces of information that go along with this. It can be cosine, it could be sine, as long as there's a number multiplying your theta value in those cases. And the 2 things that go along with it is the n value odd, or is the n value even? Alright? If the n value is odd, you're going to have as many petals as your n tells you. Like, for example, in this case, I have 3 petals. My n value is 3. Alright, so in this example, it's not exactly what this curve is, but I do know that it would be some number cosine 3 theta. That's what this is telling me, that this number multiplying theta is going to be a 3. Now if I go to my next one, there's way more petals. In fact, there's 8 petals. And because 8 is an odd number, is an even number, sorry, that's twice n. So n is 4 in this case, right? Because if n is even, I'm going to have 2 times that number of petals, and I have 8 petals here. So I do know that this equation says r equals some number cosine of 4 times theta. Then if I go to my next one, I have 5 petals. That's odd, so literally n is just telling me how many petals there are. So this would be an r equals a sine of 5 theta. And lastly, this one has 4 petals, so my n is 2. The n value here would be a 2. And the last case, circles and lemniscates. Basically, it's circles aren't that fancy. It's much like the first example we just looked at. It's just a number multiplying cosine or a number multiplying sine. And that number is essentially telling you the diameter. Right? This a value, the diameter. So now, the addition to that are these lemniscates, and it's kind of just like an infinity sign. It has the same type of idea, but it mixes together the rose curve in with this other. There's obviously exponents in here. So these are very easy to identify because they're the only type that have the exponent. So again, this a value in here represents kind of the diameter of one of the loops. Alright? So that's all the different types of special polar graphs. And actually, before we move on, if you could take a look at 9.6 and just look at exercises 1 through 4. And it talks about, certain types of equations and whether these equations are Rose curves or limations or lemniscates. So we can do that before we move on. The next thing we're going to look at when you're all set with those exercises is symmetry between graphs and the zeros of these types of polar graphs. All right, now there's 3 different types of important symmetry in polar graphs. It's either symmetry in relation to pi over 2, which is kind of like the y-axis, but in polar coordinates it's pi over 2. Symmetry with respect to the polar axis. So again, this is like with respect to the x-axis. And then lastly, symmetry with respect to the pole. So that's kind of like symmetry in respect to the line y equals x or y equals negative x. So it's the same type of important symmetry that we would see in rectangular coordinates, but we have to put it in terms of polar coordinates. So instead of y-axis, it's with respect to theta equals pi over 2. Instead of x-axis, it's the polar axis. And instead of the line y equals x with the line y equals negative x, it's symmetry with respect to the pole. Alright, and there's different ways that we can kind of test for it. To test whether something's got symmetry over pi over 2, we basically just replace r and theta with r and pi minus theta, or negative r, negative theta. And if we do that and we get the exact same answer as r and theta, then we have symmetry across that thing. And it's the same idea for polar axis and pole. We're going to replace r and theta with these different values and check to see if we have the same output. Okay, so let's take a look at an example to see what this kind of thing would look like. First of all, I can look at this equation and say, I know what type of shape that's going to come out to be. I know that this is kind of the format r equals a plus or minus b cosine of theta, which is the format for a limation. So I know that that's what this is going to be. So let's take a look here, and if I look at the a over b, that's going to be 3 over 2. So not only do I know that it's going to be a limation, but I also know that with this number being greater than 1 but less than 2, it's going to be a dimpled limation. Okay? So with that information, let's check for symmetry. Because I know it's a limation, that type has symmetry over that what we call the x-axis, but we're going to call it the polar axis in this case. And how we check for symmetry over the polar axis is we take r comma theta, and we're going to replace it with r comma negative theta and see what we get. Okay, so I go to my equation, r equals 3 plus 2 cosine, and instead of theta, I'm going to put negative theta. Ready? So I replaced r with r, that was easy. I replaced theta with negative theta. Now, what do I get? Am I still going to end up with the same equation? It's going to be r equals 3 plus 2 cosine of negative theta. What is that equal to? If I look at my trig identities, I could look back at the beginning of the book, or I might just remember, using an even identity, the cosine of a negative angle is the same as the cosine of the original angle. So yeah, if I replace both of these values, r and negative theta, into the equation, I do still get the same equivalent equation. So I do have symmetry over the polar. Okay, and that's going to help me graphing because I don't have to worry about plotting all of the points from 0 to 2 pi. Now I can just worry about making a table that's going to show theta values and r values going from 0 up to pi. Because now I know that if I go past pi and over to, draw a little circle here, because now that I know that I have symmetry over this axis right here, if I go only this far and get all of these points on the top, I know that these are just going to be mirrored, so I don't even have to worry about finding these. That's why symmetry is going to make graphing them simpler. Alright, so all that I need to do is worry about 0, something like pi over 6, something like pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, and then I can get all of my values, and I'll be able to plot the entire thing. Now, when I do, what I'm going to end up getting, this is going to be very, very, very crude, but I'm going to get something like this, where I have like a dimple over here, and this all should be a lot more straight. But I'm terrible at drawing on this thing, so I'm just going to go ahead and do one of these deals. Alrighty. I think I might have it on the next page. Yeah. So this is the same chart that I was making over there, and you can obviously see that my ridiculous drawing was not very accurate, but I got the right idea. If you were to plot all of these points, you would get all these along the top, and then we know that we have polar axis symmetry, so I can just draw it in on the bottom there. Okay? If we could try to do exercise 31 before moving on to the next part, that'd be fantastic, and we can look over that when we come into class. Alright, the next thing that I want to do is look at a rose curve and kind of analyze that with its symmetry and all of that. So what I have is 3 cosine of 2 theta. Now how do I even know that it's a rose curve, aside from the fact that it's blatantly written right up there? Well, rose curves are the ones that have, you know, multiple angles on the inside of the trig function, and they don't have any sort of exponent out here. So I know that I'm looking at a rose curve. In particular, I know that I'm looking at a rose curve with 4 petals. How do I know that? I know that because my n value here is 2. And when n is even, I know that that's going to mean that I have twice as many petals. Alright, so I have 4 petals given the fact that n equals 2. Symmetry. What type of symmetry am I going to have with a rose curve? Well, let's take a look back. I'm going to jump back to these rose curves over here. What type of symmetry is going on here? It kind of depends on whether it's even or odd, but with an even one, let's look at this one. This one has 4, so this is going to be very much like the one that we're looking at here. It has symmetry to pi over 2, it has symmetry to the polar axis, and it also has symmetry this way, with respect to the pole. So it looks like I'm going to have symmetry in basically every direction. So I could go through and I could check for symmetry in every different direction, but I know that's going to be true, and we can just kind of move on from that point, and we can analyze it from there. So I know the type, I know that it's a rose curve, I know the symmetry, another M in there, and then, at this point, I think I'm just going to jump right to my my calculator, and I'm going to type in r equals 3 cosine of 2 theta, and then I'm going to be able to see and kind of validate all of my opinions here, that it's going to have 4 petals, it's going to have this symmetry, it's going to have zeros at pi over 4 and 3 pi over 4. Because when I come over here and I say r equals 0, that means that 0 equals 3 cosine of 2 theta, and I know that you guys are going to love this because it goes back to solving multiple angle problems. So that means 0 equals cosine of 2 theta. So now when is the cosine of theta 0? Well, the cosine of theta is going to equal 0 at pi over 2 and at 3 pi over 4. Oh, sorry, 3 pi over 2. But that's not it. That's 2 theta. Are we remembering this? That means that I have to divide by 2 in both cases. So my actual theta value is going to be pi over 4, and theta equals 3 pi over 4. Hopefully you can recall how to solve this type of equation from chapter 5. If not, we might need a little bit of a refresher. And really only for analyzing rose curves. All the other ones won't have multiple angle. But this will be important for finding the zeros of a particular rose curve function. So I can find the symmetry, I can find the type, I can find the zeros, and all of that can be validated just by looking at a graph on my calculator. And you're completely open to doing that. So if we could try exercise 39 now, and that'll be the last one. We can come into class and take a look at all this stuff, and hopefully things will have gone well. So I will see you all later.